let's find the relation between Cp, Cv and R. Okay, this is what we call as the Mayer's formula. Okay, so Mayer's formula gives the relation between Cp, Cv and R. Okay, now for this one, what we do, again, we start with the laws of thermodynamics itself. Okay, so let's try to figure out what we are going to do here now. See, the first thing what we have is that, say you have, one particular thermodynamic state variables, say that is P, V and T, pressure, volume, temperature. Okay, so these are the three state variables. Now then what we are doing, we are trying to calculate what is the total energy, the internal energy, and then what is the work done. We are going to take different scenarios. Fair enough. So what we are doing, say P, V and T, this is the initial state. Okay, initial state. Now what we'll do, we'll take two cases. Okay, so the first case, so we'll make it as case 1. So case 1, we are heating at constant volume. Okay, constant volume. Now here we are heating, say the temperature change will be dt, small value dt. Fair enough. Now since we are talking about constant volume here, so what we get is that, so we are going to get the CV part, that is CV is the specific heat of the gas at constant volume. Fair enough. So this is CV. Now what are we doing? We are increasing the temperature, correct? So we'll talk into the energy and everything. All right. Now in this case, what we have, the the amount of energy supplied, what you have, so we'll call it as dq. So dq will be equal to cv into 1 into dt. Now cv is the specific heat capacity, and then 1 is the 1 mole of the gas, and dt is the change in temperature. Fair enough. So you get cv into 1 into dt. Now whenever we are talking about constant volume, the work done will be 0. Okay, this constant volume is actually an isochoric process which you guys are going to learn later on. Fair enough. Now in this case, what we are doing, since we are talking about constant volume, we are going to have cv into 1 into dt as the energy, and dw is equal to 0, because there is no change in volume. If there is no change in volume, there is no work done. Fair enough. By the first law of thermodynamics, what we have is that dq is equal to du plus dw, or you can also say delta q is equal to delta u plus delta w, like whatever we have discussed before. dw value is 0, we get dq is equal to du, or we have du is equal to cv into dt. So let's call this as equation number 1. Now let's do the second one, that is case 2. So here we'll do case 2. So case 2, what we are doing, see here in the first case we did constant volume. Now we'll do for constant temperature, sorry, constant pressure. All right. So in case 2, what we are doing, now the gas is being heated at constant pressure. All right, constant pressure. Now in this case, what we are going to have, so we have the parameter Cp. Cp is the specific heat of the gas at constant pressure. Fair enough. Now you have Cp. Again, we are going to have dq, say dq dash. Okay, so dq dash will be Cp into 1 into dt. Again, dt is the change in temperature. Now what we have, we are going to have the work done. So dw is equal to p into dv. Fair enough. Let's apply this one here. So we have dq dash is equal to du dash plus dw. Fair enough. So dq dash is going to be what? Cp into dt is equal to du dash plus p into dv. So we got this. isn't it? See, now what we have, we are changing, we are heating the gas once at constant volume, which is given by the first case here, constant volume, the second one by constant pressure, correct? Now what we have the internal energy, isn't it? The internal energy is going to be constant in both the cases. Since it's constant in both the cases, we can equate du and du dash. Let's try to do that here now. What we get is du is equal to du dash. And du is given by what? Du is Cv into dt. This is equal to Cp into dt minus P into dV. Correct? So you get Cp into dt is equal to Cv into dt plus P dV. Now here what we can do, see, two things are there in this case. So this is one, or take the other thing here. So Cp dt minus Cv dt is equal to P dV. Take dt common. Cp minus Cv into dt is equal to P into dV. Now what do we know? PV is equal to RT. Now if you try to differentiate this here, you get P into dV is equal to R into dt. So substitute P dV as R dt. We get Cp minus Cv into dt is equal to R into dt. So dt dt cancels. So finally what do we have? We get Cp minus Cv is equal to R. See, this is basically what we call as the Mayer's formula. Okay, so Mayer's formula, it relates the specific heat capacity at constant temperature, constant volume and constant pressure, and the gas constant, which is equal to R. Okay, so this is Mayer's formula.